Okay. Okay, so wow. All right. I emailed this to myself like last week when it was shared, but I know I've talked a little bit about it, but I'm going to go into a bit more depth. Today I'm actually just going to like go over the entire article. Sorry, I'm just trying to pull it up. I'm like completely out of breath. Woo. So you might be wondering like why I continue to make these like short little snippets. And a part of the reason why I'm doing it is because I want to like debunk the sort of like the confusion or you know, like the process, like what it looks like to go from idea to like paper or to like interesting technique that's like widely understood, because it doesn't start like that. And so I'm trying to do these like read-alongs to normalize like what the process actually looks like, at least for me. And this could be very specific to me, but at least from what I've learned from just being around other researchers and talking to them and just having a pretty good sense of myself, like how long it takes me to like, you know, to like understand an idea, to like sit with it, to marinate with it. What the fuck was that? That was some sap. All right. Yeah, but so I wanted to like normalize that, and I want to like really make some space for like what that looks like, so you can so you can read along with me. So I've told you, some of you, about like my interest in meta learning and this idea of like neural networks, or I'll just call them like intelligent systems that learn. And when I mean like learn, what I'm thinking about, or what I'm referring to, are systems that start with a fixed set of information. So it's like a data set, maybe it's labeled, unlabeled, whatever. This could be image, it could be text, audio, different, all types of data, but they start with a fixed set of that information and then can produce something novel, something new, something different, something that like adds to that from that information. And so I think more recently that field of thought is like coming out of like OpenAI and work that like Jeff Clune and Kenneth Stanley are doing. This is why I follow those researchers pretty heavily. But even before them, I think they started with like evolutionary algorithms, and so I feel like Clune taught the course that's about like evolutionary robotics, which I'm gonna touch on that probably like next week. But a lot of those ideas, even before that, come from this larger field known as like meta learning. And Jürgen Schmidhuber, I feel like, is one of the pioneers in that particular field. And one of his papers, like Power Play, the ideas behind that paper seem to have inspired ideas in the paper by Clune and Stanley, Poet, and and Poet too. There's like two papers, but they have like a lot more compute. So they're actually able to do a lot more than I feel like the Power Play paper in its experiments was able to do. So I want to context it with that. But so Schmidhuber put out an article like a few days ago. It's just dated like March 2021, and it's titled Artificial Curiosity and Creativity Since the 90s. So it says 1990 and 91. So I'm just gonna read over this because I feel like what he does is he puts like 10 of his like abstracts into just like one document, and so it's kind of like brushing over all of these topics that he wrote like longer papers about, and there's a very long reference list. But I'm actually gonna like breeze through this so that you can like hear these. I don't know who else is gonna like read it out loud except for me. Like I know every time these types of papers come out, I'm definitely a person who reads it, so I'm gonna do that again now. Like I said, artificial curiosity and creativity since the 90s, 91. Abstract: for over 3 decades I've published work about artificial scientists equipped with artificial curiosity and creativity. So when everyone's talking about intelligence, that's what he termed like artificial curiosity, and he's made that clear quite a few times. In this context, I frequently pointed out there are two important things in science: A, finding answers to given questions, and B, coming up with good questions. So, like a lot of the questioning systems that are out right now, like I know at NIPS, I think it was this year, it might have been last year, one of the female research scientists gave a good demonstration of like question answering systems and kind of like how they were failing a little bit. And she was trying to point that out, like saying that we have a long way to go in terms of like question answering systems, and that truly intelligent systems would be able to like generate, they would be able to answer questions like, you know, prompted questions about a particular text and ask new relevant questions that like pertain to that text. And that's like when we've seen interactions with like GPT-3, that's where it tends to fail. Like when you start to ask abstract questions to systems that are run on the back end with GPT-3, or two, like they're not able to perform very well. So that's where this like artificial curiosity is not performing very like good. It's not strong. So there's a lot of room for growth there. Okay, so A is arguably just the standard problem of computer science, but how to implement the creative part, B, in artificial systems through reinforcement learning, gradient-based artificial neural networks, and other machine learning methods. That's a question. I summarize here some of our approaches. So he's got 9 sections. In section 1, there's the 1990 Curiosity through the Principle of Generative Adversarial Networks. That paper came out in the 90s. Section 2 in 1991, Curiosity through Neural Networks that Maximize Learning Progress. Section 3 in 1995, Reinforcement Learning to Maximize Information Gain or Bayesian Surprise. In 2011, it looks like he came out with another paper to do this optimally. Section 4 in 1997, Adversarial Reinforcement Learning Agents design surprising computational experiments. Section 5 in 2006, Reinforcement Learning to Maximize Compression Progress like scientists, artists, and comedians do. Section 6, does curiosity distort the basic reinforcement learning problem? Section 7, Connections to Meta-Learning since 1990. Section 8 in 2011, Power Play continually searches for novel, well-defined computational problems whose solutions can easily be added to the skill repertoire, taking into account verification time. Section 9 in 2015, Planning and Curiosity with Spatio-Temporal Abstractions in Neural Networks. So let's start with the first one. Number 1, 1990, Curiosity through the Principle of Generative Adversarial Networks. My first artificial Q&A system designed to invent and answer questions was the intrinsic motivation-based adversarial system from 1990. It employs 2 artificial neural networks that duel each other. The first NN is the controller C. C probabilistically generates outputs that may influence an environment. The second neural network is the world model, M. It predicts the environment reactions to C's outputs. Using gradient descent, M minimizes its error, thus becoming a better predictor. But in a zero-sum game, the reward maximizing C tries to find sequences of output actions that maximize the error of M. Thus, M's loss is C's gain. So C is asking questions through its action sequences. Example, like what happens if I do this? And M is learning to answer these questions. Here C is motivated to come up with questions where M does not yet know the answer. And C loses interest in questions with known answers. This was the start of a long series of papers on artificial curiosity and artificial scientists. Note that instead of predicting the raw data, M may predict compressed versions thereof. Generally speaking, a curious system may predict abstract internal representations of raw data. There's some cool images here. I don't know if you can. Yeah, you can see those. Not only the 90s, but also more recent years saw successful applications of this simple adversarial principle and its variants in reinforcement learning settings. QAs help to understand the world, which is necessary for planning, and boost external reward. In the 2010s, the concept of 1990 became popular as compute became cheaper. The term General Adversarial Networks, GANs, is actually a new name for a special case of the principle published in 1990. GAN trials are extremely short, consisting of a single action and a single environmental reaction, like in bandit problems. In modern GAN terminology, the controller C is called the generator and the world model M the discriminator. C also, they give a couple sections, and the closely related predictability minimization. It's closely related to predictability minimization applied to images in 1996. So I'm not going to read all those external links, but there are quite a few. Okay, so moving on to idea number 2. In 1991, curiosity through maximizing learning progress. The approach of the 1990s, he links 2 papers in section 1. And I think this one is called Artificial Curiosity for AIs that Set Their Own Goals, Inventing Their Own Experiments. See my formal theory of fun and creativity and curiosity and novelty and surprise and art and science and humor. All the things, basically, okay. So, makes for a fine exploration strategy in many deterministic environments. In stochastic environments, however, it may fail. C might learn to focus on those parts of the environment where M can always get high prediction errors due to randomness or due to computational limitations of M. For example, an agent controlled by C might get stuck in front of a TV screen showing highly unpredictable white noise. Therefore, in stochastic environments, C's reward should not be the errors of M, but an approximation of the first derivative of M's errors across subsequent training iterations. That is, to prevent C from exploiting M too easily, C's reward should be M's learning progress or improvements. As a consequence, despite M's high errors in front of the noisy TV above, C won't get rewarded for getting stuck there. Simply because M's errors won't improve, both the totally predictable and fundamentally unpredictable will get boring. 1995, RL for maximizing information gain or Bayesian surprise. The simple insight of 1991, section 2, led to lots of follow-up work. One particular reinforcement learning approach for artificial curiosity in stochastic environments was published in 1995 with my former students Jan Stork and Sepp Hortritter. A simple world model M learned to predict or estimate the probabilities of the environment's possible responses given the actions of a controller C. After each interaction with the environment, C's intrinsic reward was the KL divergence between M's estimated probability distributions before and after the resulting new experience, i.e. the information gain. 10 years later, this was dubbed Bayesian surprise. Compare earlier work on information gain and its maximization through active learning without RL and neural networks. More formally, at a given time in a single lifelong trial, M has seen the entire history H of C's sensory inputs and actions so far. Now it is trying to predict the next sensory input Q given H. Suppose there are n possible values Q1 through Qn of Q. For 0 through n plus 1, n and I are natural numbers. M predicts the conditional probability of Qi given H. Then Q is really observed. Now M is trained for some time on the observations so far to improve its predictions. This yields an updated version of M called M star. M's contribution to C's intrinsic curiosity reward is proportional to this long equation. The information gain about Q. C's intrinsic joy is M's current learning progress. Now the history H is prolonged by Q, and we set M to M star such that M is ready to predict the next input observation. Again, since the controller C is a reward maximizer, C is motivated to invent action sequences or experiments that yield data from which the world's model M can still learn something. C will get bored by well-known parts of the environment as well as by unpredictable, noisy TVs. So in 2011, Bayes' optimal planning to be surprised. 2011, Bayes' optimal planning to be surprised. My student Sun Yi showed that C can optimally plan action sequences based on previous experiences such that the cumulative expected information is maximized compared to more recent work. To me, this sounds a little bit like offline reinforcement learning. I'm not positive about that, but it's kind of what I haven't read the paper, but it's what it seems like. And that's big ideas that are coming out of like the Bear blog, the Bear Lab with like Sergey Levin. Sergey Levin, yeah. In 1997, adversarial agents designed surprising computational experiments. Before 1997, the questions asked by the controller C were restricted in the sense that they always referred to all the details of the future inputs. Example, pixels. That's why in 1997, I built more general adversarial reinforcement learning machines that could ignore many or all of these details and ask arbitrary abstract questions with computable answers. For example, an agent may ask, if we run this policy or program for a while until it executes a special interrupt action, will the internal storage cell number 15 contain the value 5 or not? Again, there are two learning reward maximizing adversaries playing a zero-sum game, occasionally betting on different yes or no outcomes of such computational experiments. The winner of such a bet gets a reward of 1, and the loser gets a reward of -1. So each adversary is motivated to come up with questions whose answers surprise one another, or surprise the other. And both are motivated to avoid seemingly trivial questions where both agree on the same outcome, or seemingly hard questions that none of them can reliably answer for now. Well, that's nifty. Experiments showed that this type of curiosity may also accelerate the intake of external reward. Compare more recent related work. That is actually very interesting too. Okay, so we're moving on till we're about 18 minutes in. Section 5. This is from 2006, so we're getting more recent. Okay. Let's keep going. So maximizing compression progress like scientists and artists do. I wonder if this is power play. I'm gonna scroll down some more. No. Oh, nope, it's number 8. Power play is my favorite. That was like my introduction to his work, so I just feel like I feel all fuzzy when I hear about power play. Okay, I have frequently pointed out the history of science is a history of data compression progress through incremental discovery of simple laws that govern seemingly complex observation sequences. How to implement this principle in an artificial scientist based on a controller C and a predictive world model M. Well, the better the predictions of M, the fewer bits are required to encode the history H of sensory input observations, because short codes can be used for inputs that M considers highly probable. That is, the learning progress of the M in the probabilistic inference machine of section 3 above has a lot to do with the concept of compression progress. However, it's not quite the same thing. In particular, it does not take into account the bits of information needed to specify M and is retrained version M star. A more general approach is based on algorithmic information theory. Okay, there's like 5 papers attached to that. Here, C's intrinsic reward is based on algorithmic compression progress. Let us consider the history H up to the current input Q. We introduce some coding scheme for the weights of the model network M, and also a coding scheme for the history of all observations so far given M. For example, already in 1991, my first very deep learner based on unsupervised pre-training used hierarchical predictive coding to find compact internal representations of sequential data to facilitate downstream learning. Now, IM bits are needed to describe H without ignoring the costs of the weights of M, and IM bits are necessary to describe H without ignoring the costs of the weights of M star. Then C's total current curiosity reward for the intrinsic joy or fun reflects M's depth of insight, namely the compression progress after having observed Q. How can we measure or at least approximate the above mentioned information theoretic costs of M and M star? Over the decades, we have published several ways of learning to encode numerous weights of large neural networks through very compact codes. Here we exploited that the Kolmogorov complexity or algorithmic information content of successful huge neural networks may actually be rather small. For example, in July 2013, the compact codes of compressed network search yielded the first deep learning model to successfully learn control policies directly from high-dimensional sensory input video using reinforcement learning, in this case, reinforcement learning through neural evolution without any unsupervised pre-training. Oh, that's interesting. That was in 2013, huh? Read here how my formal theory of fun uses the concept of compression progress to explain not only science but also art, music, and humor. Okay, that's an additional paper. I'm not going to read that whole paper now. Take humor, for example. Consider the following statement. Biological organisms are driven by the 4 big F's: feeding, fighting, fleeing, and mating. That's funny. Oh, that's okay. That's funny. Some subjective observers who read this for the first time may think it's funny. It is funny. Why? As the eyes are sequentially scanning the text, the brain receives a complex visual input stream. The latter is subjectively partially compressible as it relates to the observer's previous knowledge about letters and words. That is, given the reader's current knowledge and the current compressor, the raw data can be encoded by fewer bits than required to store random data of the same size. But the punchline after the last comma is unexpected for those who expected another F. Yeah. Initially, this failed expectation results in suboptimal data compression. Storage of expected events does not cost anything, but deviations from predictions require extra bits to encode them. The compressor, however, does not stay the same forever. Within a short time interval, its learning algorithm kicks in and improves its performance on the seen data so far by discovering the non-random, non-arbitrary, and therefore compressible pattern relating the punchline to the previous text and previous elaborate predictive knowledge about the 4 big F's. This saves a few bits of storage, the number of saved bits, or a similar measure of learning progress, becomes the observer's intrinsic reward, possibly strong enough to motivate her to read on and search for more reward through additional yet unknown patterns. While previous attempts at explaining humor also focused on the elements of surprise, they lacked the essential concept of novel pattern detection measured by compression progress due to learning. This progress is zero whenever the unexpected is just random white noise, and thus no fun at all. Applications of my simple theory of humor can be found in this old YouTube video talk on the subject, which I gave at the Singularity Summit in 2009 in NYC. I'm sorry, I'm just reading that again. While the previous attempts at explaining humor also focused on the element of surprise, they lacked the essential concept of novel pattern detection measured by compression progress due to learning. This progress is zero whenever the unexpected is just random white noise and thus no fun at all. Applications of my simple theory of humor can be found in this old YouTube video. So, okay, we're moving on to section 6. Does curiosity distort the basic reinforcement learning problem? The controller model systems above, aka CM systems, typically maximize the sum of standard external rewards for achieving user-given goals and intrinsic curiosity rewards. Does this distort the basic RL problem? It turns out not so much. Unlike the external reward for eating 3 times a day, the curiosity reward in the systems above is ephemeral because once something is known, there's no additional intrinsic reward for discovering it again. That's a good point. I guess sometimes that's interesting because when we think about data augmentation, like you could have something that like a model feels like it did learn, like maybe it learns to identify a dog, but then, a dog hidden behind a tree doesn't look like a dog anymore, it looks like something else. So yeah, I don't know, that's interesting. Oh, sorry, I lost my place. That is, the external reward tends to dominate the total reward. In totality, learnable environments in the long run, the intrinsic reward even vanishes next to the external reward, which is nice because in most RL applications, we care only for the external reward. Connections to meta-learning since 1990. Section A, connection to meta-learning in the 1990 paper, already pointed out. A model network can be used not only for predicting the controller's inputs, but also for predicting its future outputs. The perfect model of this kind would model the internal changes of the control network. It would predict the evolution of the controller and thereby the effects of the gradient descent procedure itself. In this case, the flow of activation in the model network would model the weight changes of the control network. This in turn comes close to the notion of learning how to learn. The paper also introduced planning with recurrent neural networks as world models. I have not read those papers. And high-dimensional reward signals. Unlike in traditional RL, these reward signals were also used as informative inputs to the controller neural network learning to execute actions that maximize cumulative reward. This is important for meta-learning. A neural network that cannot see its own errors or rewards cannot learn a better way of using such signals as inputs for self-invented learning algorithms. A few years later, I combined meta-RL and adversarial artificial curiosity systems in the system of section 4. I'm actually gonna, oh, interesting. Okay, so this is the adversarial agents design surprising computational experiments. That's this one. Okay, so we finally made it. We're down to number 8, my favorite. This is power play. Came out in 2011. So PowerPlay continually searches for novel, formally well-defined computational problems whose solutions can be easily added to the skill repertoire, taking into account verification time. Now, when you look at the image of this entire like field of thought, I think it's an animal or something, seems well suited toward fields like robotics, especially like robots that interact with humans, because like let's say robots that interact in the human world. So if you think about like robots that maybe cook meals in your kitchen, right, but you also enter your kitchen, so they're not, I guess these could be like, you know, not digit robots, I'm forgetting some of the names, but like a robot that's just like an arm, and then like that arm maybe can like use a spatula, it can turn, it can like cook a pancake or something, right? But it also might realize like if a human comes near the stove, and it might understand to stop, or that the pancake is like done, so just stop cooking the pancake, things like that. I guess that's at least how I'm thinking about it. Again, I'm not a mechanical engineer. I'm just thinking about this in terms of what I've seen robots being able to do, and what you could, you know, hypothetically get them to control doing in the future. So anyway, my curious reinforcement learning QA systems of the 1990s do not explicitly formally enumerate their questions, but the more recent PowerPlay framework of 2011 does. Let us step back for a moment. What is the set of all formalizable questions that any curious system could possibly ask? I mean, you can't. How do you decide whether a given question has been answered by a learning machine? To define a question, we need a computational procedure that takes a solution candidate, possibly proposed by a policy, and decides whether it is an answer to the question or not. PowerPlay essentially enumerates the set of all such procedures, or some user-defined subset thereof, thus enumerating all possible questions or problems, including environments in which problems are to be solved. It searches for the simplest question that the current policy cannot yet answer, but can quickly learn to answer without forgetting the answers to previously answered questions. The computational costs of verifying that nothing has been forgotten are taken into account. What is the simplest such Q&A to be added to the repertoire? Is it the cheapest one? The one that is found first? Then the next trial starts, where the new Q&As may build on previous QAs. Compare also the one big net for everything, which offers a simplified, less strict neural network version of PowerPlay. Also, see the work from 2015 on RL robots learning to explore using high-dimensional video inputs and PowerPlay-like intrinsic motivation. The PowerPlay paper from 2011 through 2013 starts as follows. Most of computer science focuses on automatically solving given computational problems, but I focus on automatically inventing or discovering problems in a way inspired by the playful behavior of animals and humans, to train a more general problem solver from scratch in an unsupervised fashion. PowerPlay can use meta-learning OOPS, to continually invent its own new goals and tasks, incrementally learning to become a more and more general problem solver in an active, partially unsupervised or self-supervised fashion. Oh, this is interesting. So I guess this was like a paper session. OOPS is the optimal ordered problem solver. Oh, this is interesting. So when I worked a little bit on scheduling, oh man, no, it's like escaping me. I'm like starting to forget. So when I worked a little bit on scheduling is a pretty solved problem in operations research. That's what I was thinking. Okay, so like there's a lot of people who study like operations research for like scheduling and like routing and like and so this problem of like the optimal ordered problem solver, it's giving me like operations research vibes. And they have like they have programs like Google has OR tools, which is like a really cool solver, right? It like has a lot of the well-defined operations research problems are available to just like run in OR tools. But I will say like it's very hard to run OR tools on like just a collab notebook or like your own computer. Like I think you do need to like rent a server and have a bit more powerful compute, because like I wasn't able to like run it like on my own computer. It timed out many times. Okay, so then we've got number 9, planning and curiosity with spatio-temporal abstractions in neural networks. Our approaches to artificial curiosity provide a predictive world model that can be used for planning. The recurrent controller worlds model system of 1990 focused on naive millisecond by millisecond planning, trying to predict and plan every little detail of its possible futures. Even today, this is still a standard approach in many RL applications, like RL for board games such as chess and Go. My more recent work of 2015, however, has focused on abstract, hierarchical planning and reasoning, continuing the work of 1997 summarized in section 4 above, and earlier work on hierarchical RL since 1991. Guided by the algorithmic information theory, I described recurrent neural network-based AIs that can be trained on never-ending sequences of tasks, some of them provided by the user, others invented by the RNN AI itself, in a curious, playful fashion to improve its recurrent neural network world model. Unlike the system of 1990, the RNN AI learned to actively query its model for abstract reasoning and planning and decision making, essentially learning to think. That's really cool. Compare also our recent related work on learning hierarchy structured concept spaces based on abstract objects. The previous ideas can be applied to many other cases where one RNN-like system exploits the algorithmic information content of another. They also explain concepts such as mirror neurons. See also the work with David Ha of Google in a world model that extracts compressed spatio-temporal representations which are fed into compact and simple policies trained by evolution, achieving state-of-the-art results in various environments. Agents with adaptive recurrent world models even suggest a simple explanation of consciousness and self-awareness dating back 3 decades. References. Okay, so it's like every single piece here that was cited, there were like 3 other, probably more than that. I mean, there's like 5 or 6 other papers that were cited that went into depth on like where these ideas came from and like how we got here, and I just have not read all of that back work. And I've been saying for a while, I'm glad that he wrote this and kind of like you know, referenced the other articles that he's like thinking of when he's reading this. I honestly feel like maybe this, I mean, it probably won't happen like this year, but I don't know, maybe like next year. I think that like I may just take some time and just like actually get through all of this. I mean, I honestly haven't had the time to do that, but there's so much, honestly. There's so much here. Like what I have open right now is the planning and reinforcement learning with recurrent world models and artificial curiosity. And I can't remember where I came across the world models paper. I think I came across it in one of Peter Beale's talks where he had the slide up and then said, you know, check out the GitHub page. And then there's like a GitHub page that just talks about the world models paper, because I guess the world models paper was a big like it was like a historic project in terms of like progress in that field. So I am familiar with that, but it looks like this idea came out way long ago. So that work is like an addition to this that came out in the 90s. So yeah, so that, I mean, that's all I wanted to get through for today. Those are like the big ideas. And yeah, thanks for like watching or listening.